Welcome to Dr. Boxy Teaches Electromagnetism. In the previous lesson, we introduced the concept of the electrostatic potential. Today, we will look at the concept of work in the context of electrostatics, and we will see that there is a relation between the electrostatic potential on the one hand and the electrostatic potential energy on the other hand. So let us get started. We consider a collection of charges in space, and we now know that they create an electric field and therefore also a corresponding electrostatic potential. And in that field, we take a test charge, which I represent by capital Q, and I want to move it from a point A to a point B along some trajectory. The question that I'm trying to answer is, how much work does this require of us? Well, the definition of work is force times displacement integrated over the trajectory, so it's a line integral. But which force am I supposed to plug into this expression here? Well, if we think of a pen in the gravitational field, gravity tries to accelerate it downward, which means that if I want to make sure that it does not accelerate, I need to exert a force negative mg or mg upward to counter the force caused by the field on the pen. Of course, if I want to accelerate it, I would need to exert more than that, but the bare minimum I need to do to be able to control it without accelerating it would be to counter the effect of the field. Well, the same thing is true in the case of electrostatics here. The bare minimum we would have to do to make sure that we can move it without accelerating it along a trajectory would be to counter the effect of the field, the force that the field causes on it. Now, the force that the electrostatic field exerts on capital Q is the Coulomb force, which is Q times E, which means that the force that we would need to exert on the test charge at the bare minimum would be negative QE to counter the force of the field. And so that's what I will plug in to the expression for the work, and I find this here. And remember now that negative integral of EdL is the potential difference, and so we find this expression. In other words, the potential difference VB minus VA is the work we need to do to move the particle from point A to point B, the amount of work we need to do per unit of charge. Remember also that we said we would often take infinity as the reference for the potential, so the point at which the potential is by definition equal to zero. And if we now want to bring in the test charge from infinity and place it at a point represented by the vector r, the amount of work we would need to do would be Q times VR minus V infinity, where V infinity is by definition zero. So we're left with Q times VR. Now, in mechanics, we define the concept of potential energy as negative the work done on a particle when it moves from some point to some other point. That is the change in potential energy. That's how it's defined. Which means that in this sense, the potential can also be thought of the amount of work, in other words, the potential energy per unit of charge. Now, I want to make very clear, there are two words here. You have potential on the one hand, and you have potential energy on the other. They are related through this relation that I wrote here, but they're not equal to each other. Potential has units of volts, potential energy has units of joules. So make sure you don't mix those two. They are two different concepts, though they are related to each other. Imagine now we start with empty space, and we want to bring in charges from infinity and place them according to some configuration in space. The question is, how much work would that require of us? Well, for the very first particle, it doesn't require any work because there is no field it has to fight against. So I'm bringing in a point charge Q1 from infinity and I'm placing it at R1, and that requires no work at all. Now I bring in a second charge, Q2, and I want to place it at R2. But doing that does require work of me, and that amount of work I call the W2. And why does it require work? Well, because it has to fight against the field created by Q1. And we saw on the previous slide that the work required would be the charge that is being brought in, so Q2, multiplied by the potential through which it is moving, the potential of Q1, which I called V1 here. And we also saw in the previous lesson that the expression for this potential, assuming that we take the reference at infinity and that Q1 is a point charge, which we are assuming it to be for now, is 1 over 4 pi epsilon naught times q1 over the magnitude of the separation vector, curly r12. So this is the amount of work I need to bring in charge number 2 into the configuration. Now I bring in a third charge, and it has to fight the field created by q1 and q2. And so the work done to bring in a third particle and place it at the position r3 would be q3 times the potential created by charges 1 and 2. And because of the principle of superposition for potentials, we know that it's simply the sum of the potential created by q1 and that created by q2, which means that we get this expression for the work necessary to bring in a third charge. Similarly, if I bring in a fourth charge, I would get this expression, and we can keep on going. But if we keep it at 4 charges for now, the question is, what is the total amount of work needed to bring in all 4 charges and place them according to some configuration in space? The answer is, it's the sum of W2, W3, and W4, which gives us this expression here. What do we see here? Well, we have a 1 over 4 pi epsilon naught, which is common to all terms, so I just brought it to the front. And in the denominators, all the denominators are all the possible separation vectors we have in our system. And in the numerators, we have all the corresponding products of the charges. Now notice that I ordered them in such a way that the first one is always less than the second one. So if I write it as qi, qj divided by curly r, ij, I chose it such, I ordered them in such a way that I is always less than j, just to avoid double counting. And so in general, if we do it with n particles instead of 4, the expression would look something like this. It's 1 over 4 pi epsilon naught times a sum over all possible pairs qi, qj divided by curly rij, where, again, to avoid double counting, I assume that j has to be larger than I. But what I can do is rewrite it a bit. And I will rewrite in such a way that I do allow double counting. So I will not assume anymore that j is larger than I, but I will divide the expression by 2. So I still assume that j is different from I, but now it can be either larger or smaller, which means that every pair qi, qj is counted twice, once when I is larger than j and once where I is smaller than j. But because of that double counting, I correct for it by dividing the whole expression by 2 again. Now, as a next step, I will take the 1/2 and leave it at the front. I will take the sum over I and bring the qi in front of the sum over j. So I get this expression here. So I brought the sum over I with qi to the front, and everything else I left within the parentheses. Now notice that that expression within the parentheses is exactly the potential created by all the charges except for the ith one. So V here in this expression is the potential created by all the particles except the ith one. And notice now that because we're summing over I, there is no question anymore about in what order did we bring the charges. It simply does not matter. Every charge is summed over, I goes from 1 to n, and it has a term qi times the potential crossed by all the other ones, no matter whether they were brought earlier or later than qi. This is one way to write the work necessary to bring in those charges from infinity and place them in space in some configuration. Now this expression that we just found is the amount of work necessary to bring in the charges from infinity, assuming that we're considering discrete charges. But if we're looking at a continuous distribution of charges, we're bringing in continuous charges and creating a continuous distribution of charge in space, we would need to replace this expression by a continuous version of that. What does that mean? Well, first of all, the sum in the continuous case would be replaced by an integral, which is the continuous analog of a sum. But qi, the charge, would be the charge density rho, the volume charge density, times d tau. If we're in 3 dimensions, it would be sigma dA, the surface charge density times a portion of surface dA, or in one dimension, it would be lambda, the linear charge distribution, times dl. And so we get these three expressions depending on whether we're working with a continuous charge distribution in 1, 2, or 3 dimensions. Those are the analogs of the expression I wrote on the top left of the slide in case we're looking at continuous charges. And now I want to rewrite these expressions, and I will do that for the one in 3 dimensions for the upper one of the three. So I start with the expression W is 1/2 times the integral of rho v d tau. Remember that the v here is not the volume of anything. The v in this expression is the potential. Now we also know that the rho is related to the electric field via Gauss's law, which means that the rho in the integral can be replaced by epsilon naught times the divergence of E, which is this expression here. And now, what can we do with this? Well, several lessons ago, we looked at the way to integrate expressions involving scalar and vector fields. And one of the things we saw there was that there was an expression for integration by parts. And the expression I wrote here in small font at the right was one of those expressions where the integral on the left-hand side is over some volume. The integrals on the right-hand side, well, the second one is, again, a volume integral over that same volume. And the closed surface integral, the first one on the right-hand side, is a surface integral over the boundary of that volume. And if we apply this expression, this formula for integration by parts, for what we found for the work, we get the expression I have here in the middle at the bottom. And finally, notice in the second integral we have a divergence of V, and we know that the divergence of V, by definition, that's how we define V, is equal to negative the electric field, which means that we get this expression for the work necessary to bring in charges from infinity and create a continuous distribution of charge. But we can still rewrite it a little bit. So these are the three expressions we have: the discrete version, the continuous version in case we're looking at a 3-dimensional charge distribution, and the rewritten version which I wrote here at the bottom. Now, the sum is, in the discrete case, we are summing over all the charges that are being brought into the system from infinity. The integral in the middle expression, what are we actually integrating over? Well, we are integrating over all the charges that are brought in, all the continuous charges which are being brought in, which means that if we have a continuous charge distribution there, it is an integral over the volume in which that charge is sitting. But notice that if we were to replace the volume integral of rho v d tau by an integral of rho v d tau but over a larger volume, it would not change anything, because rho is 0 outside of the portion of space where the charge is sitting, which means that I may as well increase the volume. Once I have a volume that contains all the charges that were brought in from infinity, increasing the volume will not affect the result of this integral. But that means that if I look at the bottom of the three expressions, the ones with the two integrals, what are we integrating over? Well, the e squared term is being integrated over that same volume, and the closed surface integral is integrated over the boundary of that volume. Now, if we increase the volume, according to what I wrote at the top right, it shouldn't affect the final result. In other words, it shouldn't affect the expression for W. But if we increase the volume, e squared is a non-negative expression, which means that it can only increase as we increase the volume. And to compensate for this increase, the first term, the closed surface integral, has to decrease. Now, why does it decrease? Let's see if we can understand, at least qualitatively, why it would decrease. Remember that if we go far enough away from the charges, the electric field itself is proportional to 1 over r squared, and the potential is proportional to 1 over r, which means that the product of E and V is proportional to 1 over r cubed. While the integral itself, or rather the surface area, it is proportional. As we increase the surface, this increases as r squared. The surface of a three-dimensional shape increases quadratically with its radius. That means that, qualitatively speaking, E times V times dA decreases as 1 over r. So this here is proportional to 1 over r, which means that as we increase the volume, the relative importance of this term, of the boundary term with respect to the integral of E squared, decreases. And as the volume becomes larger and larger and larger, that expression will go to 0. And if we take the volume to be all of space, we find that the work is simply epsilon naught divided by 2 times the integral of E squared d tau, where the integral in this case is taken over all of space. The boundary term vanished in this case. Let us now use these expressions to calculate the energy of the same hollow spherical shell that we've looked at in the previous lesson. It has a uniform surface charge density of sigma, a total charge q, radius capital R, and we choose as the reference for the potential infinity. Now we have two different ways of calculating this energy, the work, and they will use integration over different regions of space. Either we use this expression where the integral goes over that part of space where the charges are sitting. In this case, it's on the outer shell, on the outer surface of this spherical shell. Now we've seen, remember the V in this expression here is the potential, and we saw last lesson that the potential of a hollow spherical shell is given by these expressions here. And so what we need is the value of V on the shell itself, which means that it has a value of 1 over 4 pi epsilon naught times q over capital R. In other words, it's a constant. And so as a whole, it can be pulled out of the integral, and we're left with the integral of sigma times dA, which by definition of sigma is equal to the total charge of the shell. And so we find this expression for the work necessary to bring in the charges to create this hollow spherical shell. A different way of calculating this same work is using this expression, and for it we need the electric field of such a hollow spherical shell, and we've seen a couple of lessons ago that this was the expression for it. Now notice the integration here is over all of space, but the electric field within the shell is 0. In other words, we're left with the integral only outside of that spherical shell. And outside that shell, the expression for the electric field is the one that I wrote at the bottom right of the slide. And so E squared was replaced by 1 over 4 pi epsilon naught times q over r squared r hat squared. And d tau, a tiny portion of the volume of space, is r squared sine theta dr d theta d phi. It's a triple integral. And we brought the 1 over 4 pi epsilon naught squared comes out of the integral. Q squared also comes out of the integral. Notice we have here r squared, which itself is squared, so we have a 1 over r to the 4th power, but multiplied with an r squared here gives us net 1 over r squared. And the r integral goes, because we're only integrating over the region outside of the spherical shell, the integral goes from r to infinity, and the integrals of theta and of phi go as they always do in spherical coordinates, from 0 to pi for theta and from 0 to 2 pi for phi. The phi integral is simply equal to 2 pi. The theta integral, we've seen it a couple of times, is equal to 2. The r integral, it's 1 over r squared integrated, is equal to negative 1 over r. And that evaluated at infinity gives 0, so we're left with 1 over capital R. And that gives us this same expression using a completely different approach. Notice the stark difference there is between the two kinds of integrals we consider here. The integral in method 1 is an integral over that region of space where the charge is sitting, in this case the outer shell of that sphere. The second method is an integral over all of space, not only where the charge is sitting. And that brings us to the question, where is the energy stored? Because we've calculated the energy work in two different ways. Either we consider the charges themselves, and we integrate over that region of space where the charges are, or alternatively, we are integrating over all of space and considering the field everywhere. So is the energy stored in the charge or is it in the field? Well, at this point in time, as we're looking at it now in electrostatics, the answer is it doesn't matter. Whether you want to philosophically think of it as being in the charge or in the field, you get the same results. So from a physical perspective, there's no difference between them. Now, it will turn out later on in physics that it does make a difference, and the better way of thinking about it is of the energy being stored in the field. But that is something that only turns out much later in physics. At this point in time, you may as well think of it as being stored in the charges. Whichever one you use, you will get the same result, W. This is what I wanted to tell you about work and electrostatic energy. Next time we will look at conductors, and more specifically at conductors in the electrostatic situation. I'll see you next time.